I'm one of the guys. Unfortunately, I will be there only later during the program. I will basically give a review very much along the lines of what Giang has already reviewed, I would say, about what, in a sense, what motivates the program and the progress made in this, the connection of these two areas. So I'm Giuliano Giacalone from the University of Heidelberg. And I would like to first say that this program is essentially in the context of a considerable amount of activity at the intersection of nuclear structure and energy nuclear collision. So we have quite a bit of meetings already in 2022, and others at this INT program. Just a few other points. In the next initial stages conference in June this year, we'll have actually a track related to nuclear structure, which is the first time for an high energy nuclear conference. We provided input to long-range plans in the US and the EU with Zhang Yong and many other people. You can find this actually at this link. And with Yo Zhou, who is the main say person driving these efforts in the ALICE collaboration at CERN. And then, for instance, we also have a topical issue on the intersection of these two areas, where we will be collecting about 20 papers in 2023 on EPG, this led by Thomas Duguay, Saclay, and Vittorio Soma, also from Saclay, and again, Yo Zhou. So this is a sort of new research direction which is attracting attention, seems to have a bright future ahead, I would say. So just to, then my goal is basically to tell you how we got there and what we're interested in. And I will have basically to say a couple words about high energy nuclear physics and the relevant parts of that, which, let's say, the parts of that which are relevant for my discussion, then how nuclear structure enters into high energy nuclear physics, manifestations of nuclear shapes in high energy experiments, just to basically confirm or let's say, validate, let's say, the whole thing works, and then prospects about what could be done in future. There are many interesting directions which are open. So this will be a lot of stuff actually. So I will not will be maybe a bit fast, but most of this will be recovered again. Let's say covered again during the program in the coming weeks, and so this is perhaps certain things just to give a flavor. So high energy nuclear physics is the effort of studying, as Giang said, matter which is created in the extreme conditions which are created when you collide nuclei at the highest possible energies. So the machines which do that, these are the largest accelerator facilities in the world. So one is the RIC, which you'll know, which is dedicated to collisions of nuclei. This is where the proton plasma was discovered. And then there's also LHC, which does this about 1 month per year. There's the ALICE collaboration again, which is entirely dedicated to again collisions. Overall, this is a very big experimental program, and I think this will go on for another, I don't know, 4 years or 5. At LHC, this is planned to the nuclear collision program is planned to continue until the shutdown of the machines in the next 20 years probably. So again, the idea is to study emergent phenomena and strong interaction matter in the regimes which are reached in these collisions, which are the regimes, of course, of very high temperatures, essentially. So just briefly, the snapshot of a collision, and I will go back to this picture in a moment, is something which will be seen like this: two nuclei which collide at certain interaction points. This is basically what happens, what we understand in the plane orthogonal to the beam at the time of interaction. And the idea is that after a short while, very short while actually, 1 Fermi over C or so, this system essentially becomes a sort of thermalized medium, which you can then treat macroscopically as a macroscopic system in terms of effective fluid description. So Zhang Yang has already anticipated this. So we don't try to describe this process, let's say, in first principle perturbative QCD. That makes no sense. But you can study emergent properties of this matter. So you invoke macroscopic qualities like energy density, pressure, transport properties, which are very important in viscosities, which are essentially properties of QCD. This is, of course, Coulomb plasma is the thing that characterizes this mostly is the equation of state, which is something which can be evaluated from the lattice and which is visually is confirmed in the experimental data. So the fact that it has a large number of degrees of freedom, which is due to the liberation of color and flavor degrees of freedom in the system. So this is really what defines from the QGP. Relevant temperature, for those who are interested, is something about some trillion Kelvin. So this is the hottest fluid as produced in the early stages, if you want, the cosmological expansion, for instance. So as Giancarlo said, we want to study, I would say, the whole process with a focus on this piece of matter. But this implies understanding as well the initial condition of the system. So what happens at the level of the collision, and this will be the focus of my talk, and I would say it's probably the entire program as well. So the initial condition. Let's say before I go into details, I would like to say then that with reference to the initial condition, the way we understand the ion collisions again is not is yes.
There's a person in the room.
Yes.
Can you specify exactly what you mean by initial? Do you mean tau equals 0 minus just before the collision, or tau equals 0 plus but just after the collision?
Ah, that's a good question. I would say 0 plus, event by event.
Yes. I think the issue of how to get from tau 0 minus to tau 0 plus is actually highly non-trivial.
Yes, but I would say what you want to, you want to reconstruct 0 plus, then, well, it's the whole thing. But yeah, maybe I can say something more here. Avian collisions, indeed, as I said, is not something you understand from like in a perturbative, like in the proto scattering at high energy. Like you want to understand the process as a tower of effective descriptions, starting from basically the entire process is then done in this way, and I think we've been very successful in defining effective descriptions appropriate for various stages of the process. So you start with two nuclei that, if they were colliding at very low energy, they would look like this. Now, as you collide them at ultra-relativistic energies, in fact, you will see more something like very Lorentz contracted in the laboratory frame. And already at this level, you may wonder, okay, how should I describe matter in general? That looks like this. So there is an effective theory of QCD of high energy QCD called the cold glass condensate, which studies this, and uses some classical approximations, for instance, for the small degrees of freedom in your chunk of matter, and the nucleus or proton, anything made by two gluons. The subsequent stage right after the impact, so this would be the zero, if you want to go back to the question, the zero minus. The 0 plus is something that you can still describe in this framework as an effective description of highly coherent occupied gluon states. It was the plasma, and it's something actually quite important because it is, as far as I would say, it's the only theory in the sense that it gives us a prescription to get some knowledge about how the energy density is actually deposited in a sort of first principle setup. So this would be like the energy density, average energy density of the system in a collision, in a bunch of collisions, and this gives you some insights on how that occurs actually. Now, moving on, this phase lasts very shortly, and then you actually start your more going to a particle description where you can then have effective theories of QCD for a kinetic theory, which will lead then to it's the subsequent, you want first Fermi over C of expansion, which leads to thermalization. So this is essentially a sort of transport calculation with the QCD motivated collision kernel, if you want. And then once this is over, you can go into finally your viscous hydrodynamic description for long wavelength modes, which involves an emergent pressure gradient and emergent properties of QCD that you would like to reconstruct, like the viscosity and such. Now, I think the main theme of this INT program, essentially what this research business I'm talking about, is that we are now at the level of, I would say, model to data comparisons are good enough these days that we can really think to refine this picture by adding somehow the zero, I would say, I wouldn't call it 0 minus, maybe let's say minus in time equal minus infinity piece, which is how we have to use effective theory of QCD for spatial distribution of large X degrees of freedom. So in the nuclei that we are going to boost. And so this, of course, now then involves nuclear structure. That's why you have completed the picture. So this is eventually what we want to do. I would say the goal, to refine the overall picture with this component. Now, again, how do you, so essentially all you measure is just distributions of particles in the final state. How do you go back to from plus infinity to minus infinity? Well, the point is that always these particles, you have to be able to reconstruct stuff from that. But this is essentially easily done, I would say. So you measure lots of particles, like in this picture of the star collaboration, and low momentum particles, which are, let's say, the bulk. Most of these particles sit at low momenta. Effectively, are those that follow this hydrodynamic expansion and contain the information that you want to reconstruct. So you don't see a cold-blown plasma, right? That's too small. However, from the analysis of let's say, how explosive the expansion is, which is basically how fast this particle travel and what the momenta are, and the anisotropy distribution in angle, which is also something that we can analyze very precisely, we can reconstruct information about the initial state. So these are the two fundamental ingredients for us to try to go from the particles to the actual shape of the core gluon plasma. And so there will talk by Jean-Yves. I think tomorrow we'll discuss more about this. The physics is essentially very similar to what is done in the context of cosmology, then, where you measure some, for instance, temperature map, which is characterized by anisotropies in a multiple expansion, and you want from those to reconstruct the initial perturbations to understand the primordial universe. In heavy ion collisions, then you measure these. Let me go back for a second. You measure these Fourier anisotropies, which are these anisotropic flow coefficients, break coefficients. You have a spectrum of this. This is the order. This is pretty much the best you can do. Maybe we'll push this to 10, maybe in the next LHC runs, but that's probably not going to add much. Yeah, from the highest and most precisely measured ones, you precisely try to go from a distribution of particles back to the primordial condition of the system, which is essentially a lumpy distribution of energy, which comes from the collision of the two nuclei. So this is pretty much the endeavor. And the reason why you can do this, precisely map what you observe to what's there at the beginning, is just essentially a consequence of, we'll say, hydrodynamics, the emergent description, which leads to essentially deterministic evolution. And just again, the emergence of the pressure gradient force, which creates a very simple connection between what's observed in the final state, what is there at the beginning. So final state, you measure particle distributions, and depending on how fast these are expanding, you can make relations with the, make relation with the initial geometry. Once again, simple example, for instance, a fixed particle number, a system which is closed within a smaller volume. So this is smaller than this one, as a larger pressure gradient. So more density, more explosive expansion, and more PT in the final state. A system which is enclosed in a deformed container as an imbalance of pressure gradients, and final state, you will see something which is deformed as well in momentum space. If you have something elliptical in the beginning, then you will have elliptic flow, so an elliptic distribution of momenta, and same if you have a triangle, you have a triangular flow. And these are, so these flow coefficients, Vn, V2, V3, and the amount of momentum of these particles then allow you to reconstruct the shape and the size of your QGP from the experimental measurements. And this is very straightforward. And this is what has, I would say, led to the progress in the phenology of heavy ion collisions for the last couple of decades. And very good. So this is pretty much the point, reconstructing shape and size of QGP from experimental data. So this is then when nuclear structure comes in. Because to shape your QGP, you need some input from the two, so what you're colliding, of course. So, and the way we, the picture that we, let's say, established in last 2 decades is say, of heavy, would say, theoretical comparison and phenological studies is something like this. So the idea is that the two nuclei are completely destroyed in the interaction process, and this leads to effectively sort of quantum measurement of the positions of all the scatterers that are placed inside the nucleus. So whatever scatters will be essentially resolved by the interaction, and so you resolve essentially the distribution of nucleons at the time of scattering. So it's an effective collapse of the wave functions, if you want. What you understand is that scattering essentially is within nucleons. So the nucleon positions are what really matters for us. I like to make an analogy with the work that is done, for instance, here in Heidelberg, in the some collaborators in the works on ultra-cold atom gases, where they can actually make mesoscopic systems with the control number of particles and then take images of this. And they can, for instance, make this image of what would be a gas of 10 lithium atoms at some time. And this is pretty much the way we understand what happens in a heavy ion collisions event to event. There is an effective collapse of all these positions that is sort of imaged by the interaction. Now, very good. So how do you get the nucleon positions then? This is where you have to record the nuclear structure. The simplest thing, which works pretty well for a system like lead-208, is a mean field essentially approach, where you just try to put see the problem as a problem of independent particles, which are inside some common potential. So this is I would say the best phenological answer is a Wood-Saxon potential of this kind, which is what we use in all the simulations. And you just assume that you have independent particles in this potential, And this gives you a model of a nucleus that you could use just to generate again this kind of profiles on event-by-event basis. So I guess we will hear more about this this week, probably by people like Benjamin Bali. If you try not to do something so simple, but to get some actual nuclear interaction from effective potentials, then you enter the business of energy density interactional theory, which is what we mainly use for the moment for as an input for heavy ion collisions. So if you just do this mean field description, which is essentially just the fact that it works essentially justified the what we call the Glauber Monte Carlo approach, which is precisely this picture that I'm showing here, if you want. Then you get something which works, and this confirms somehow that the picture is consistent. One ingredient I should add is that the nucleus-nucleus interaction does not really mess up the geometry of the system a lot, in the sense that the shape of this area of the interaction region is then very much reflected in the shape of the, if you want, large-scale structure of the core-blown plasma. See, this is essentially true in all viable models of energy deposition that we have. And then if you then do this prescription and then go to the experimental data, so these red points are basically state-of-the-art hydrodynamic simulations. This is extremely precise phenomenology. For this V3, for instance, is something which is entirely generated by these fluctuations that you see here due to the nucleon positions. And we just get very naturally a very good description of the experimental measurements, which means that this picture is very, very consistent. And it seems to work. Now, yes?
Yeah. What kind of direct experimental evidence do we have that this works? I mean, what you're showing is that you put some assumption in at tau equals 0, and then you measure something at tau equals plus infinity, and you have a description that works. But to what extent do we know the precision with which this description works?
Well, I guess
you talk about, and I completely agree at a rough level with you, that the collisions are a measurement of the positions of the nucleons. But what is the resolution of that measurement, and does it depend on the observer? Is there a different resolution that I have to fold in when I talk about the evolution of the anisotropic flow coefficients versus when I talk about jet production, hard parton production?
Well, certainly well, if you want to study, I guess, abstraction, you have to know better where specific scatterers are located. But I would say the resolution is dictated just by the collision energy, and so this is one question, which will essentially tell you how much you can resolve inside this nuclei and how much you can probe. But I would say for the evidence of the picture to work, I think if you build a model like we do these days, and you can quantify the uncertainties, then you can essentially see how far this picture can go and where it breaks up. And if it's wrong, at some point it should break up. And I think it's the way to go.
Yes, but I think this workshop should talk a little bit about how you are going to do that.
Well, we can discuss, yeah. Yes, but thanks for the comments. This is very useful. But this is the picture. The question then is precisely that if you want to, so this is this very simple model I described works well for lead-2-8, but as soon as you have nuclei for which you are supposed to take into account strong spatial correlations, then again, as you probe essentially nucleon distributions in this way on an event-by-event basis, then you should be able to include all correlations. And this means that you cannot just live in principle with the spherical mean field model. That's something that doesn't work. You in principle you would input for all essentially 2, 3 A-body correlation functions, spatial correlation functions in your system, which is something that is not really known. But low energy nuclear physics can help us, and this is what we do, because what is driven, I would say, also phenomenology low energy is the notion of intrinsic shapes, which is a very convenient way of encapsulating correlations of nucleons.
So, maybe
yes.
this question also not only for you, but this is the two-body correlation function, but there's a four coordinate appears, right? In principle, I mean, it is a two nucleon correlation, but it's actually there are four coordinate. is this really like, you know, if you write down the correlation itself, where the nuclear, the C plus and C minus, C, and they do not have the same coordinate, this really, it's the mathematics actually shows up just like a two-body correlation function after you average over, let's say, project out or the wave function, or this is more than that. Because, you know, when we talk about the two-body correlation function in our language, they're really like, there are only two positions, right? Or two momentums. I don't know how this is related to what we do in Hanyang collision. Maybe I didn't formulate my question.
Yeah, I'm not sure I understand exactly what you mean.
But yeah.
Yeah, I'm not sure I understand what your point is. Sorry.
No, what I mean is once you do the projection, you still have four coordinate, R1, R2, R3, R4. It's not like doesn't look like a two-body correlation function.
He says it looks like a four-body correlation function because there are four coordinates.
Yeah, okay. This is how it's defined in code.
It's like a Wegener function, right? Almost. Where the momentum shows up somehow.
I don't know, but it is certainly a function of four variables. So
yes,
it's a function of four variables, but
4-point function. So why do we guys call this?
Yeah, but this is, I don't this I understand, but someone else can comment on why this is called like this, because
there are two particles. But I think what you mean is you want the diagonal paths where you have one. I mean, what Giacalone said. I think you just used to looking only at the diagonal part, so to what we call two density.
So diagonal would be like R2 and R3 are equal, and R1 and R4 are equal. Yes.
But this intrinsically contains momentum, right? Because the fact that R2, R1 not equal to R3, for example, there's a momentum component in this. But they're not
Well, I think we should have a larger discussion later on how this quantity enters into anything that you can measure.
Yeah, maybe I can comment that we don't know at the moment how to do like heavy ion collisions with just correlation functions and not with just sampling of nucleons. I think this would be something extremely useful if this was figured out, for instance, because I think mainly nuclear structure theory can compute correlation functions rather than sampled configurations. There are a couple of frameworks that do that, and it would be indeed good to relate more in a more formal way how correlation functions like this, which are inside the nuclei, relate, for instance, to correlation functions of the energy density of the initial condition of heavy ion collisions. This is something which has not been done yet, and it's probably a good time to do that. So I think there's this. It will be really interesting to understand better how correlators of this kind enter, in fact, the energy deposition, provided some model of energy deposition at least. So, but okay, then the idea is that whenever you have these sort of long-range correlations or collective correlations, then you resort to the notion of an intrinsic shape, such that you can still somehow keep your mean field approach, but within a deformed potential, and then you can see sort of heavy ion collision as nuclei which are shapes which are sort of randomly oriented at the time of the interaction, and then the collision selects one of these orientations. This is how this would come naturally. And so the idea is then that you can, if you have nuclei that are deformed, that are not lead to weight, for instance, you can just keep again the same model essentially, but you introduce these shapes which will encapsulate these correlations of nucleons. And this can be, this most standard way, I think, is this spherical harmonic expansion, where you introduce quadrupole deformation, octupole, hexadecade, and so on, and also very important breaking of axial symmetry, which leads to, if you want, different axis for the ellipsoid, which is quantified by this gamma parameter, which is something which tells you to go from oblate and prolate nuclei, etc. All these shapes, I always quote this sentence by Michael Bender, which is saying that these shapes are not really observable directly. So these are sort of artifacts, but their imprint is there everywhere in nuclear phenomenology. So it makes sense that we see this as well in high energy nuclear collisions, which are very precise nuclear experiments. And so this is the model. This is I hope this is clear to some extent. Will be reviewed by some other people, I guess, in the program. But maybe. So what I'd like to convince you then is that we see essentially evidence of these shapes in high energy experiments in a sort of spectacular way. So one way because we can do it. One reason why we can do it is that we have enough species these days. So we have not only lead, which is the main species at LHC, or gold, which is the main species at RIC, which are fairly spherical, I would say. But also now, again, more species. This was anticipated by Zhang Yong, xenon at LHC, uranium at RIC, and these isobars, ruthenium and zirconium, recently released at RIC as well. So there is the natural question then is whether the whole construction of the high energy model, let's say, survives when you include the precise nuclear structure input for the non-trivial nuclear distribution of these nuclei. Of course, then there's also the question of whether the expectations from low energy are also compatible with whatever you serve at high energy. So this, I think we are fully there yet, but this, of course, is something very interesting to investigate in the future. So let's see then if we can understand consistently what happens at in high energy collisions of nuclei that are like deformed. The second reason why we can do all of this is that we have now established observables that gives us a unique sensitivity to whatever goes on with the shape of the nuclei. So the simplest is essentially how the interplay between the air, the size, and the ellipticity of your Coulomb plasma, which is something which, if you think about a collision of prolate nuclei, like these objects, are they non-trivially correlated in the sense that if you have a collision like this, you generate a circular area which is small. If you have a collision like this, you have an elliptic area which is larger than this one. And if you have both in your sample, then if you have a correlation between the V2, so the elliptic anisotropy, and the mean PT or the area, then you have something non-trivial, which happens just because you have these deformed objects. So the ellipticity of QGP in general is positively correlated with this area when you have significant deformations at play. And so these are pretty much the main tools. We can see what happens. So the most obvious is comparing uranium collisions with gold collisions. We measure precisely a shape size correlation. So this is now discussed extensively in the ion collisions. V2 mean PT correlation. There is a very strong qualitative difference between gold and uranium collisions as you move to the limit of fully overlapping shapes, the very high multiplicities. So you see the trend, which indicates precisely this positive correlation between area and the ellipticity of the QGP, which is not there for gold nuclei. And it's a completely model-independent signature of the input of this strong prolate deformation, which is then something observed. I would say that recently, that as a consequence of this prolate deformation, we were also able to spot effects of the hexadecapole. This is actually work in progress, but I think it's nice to discuss it here. If you look at all the literature comparing hydro to data in uranium collisions, there is a sort of tension at the level of this ratio. So how much the deviation you get with respect to the gold, let's say, a baseline. And based on this relation, which is in fact true at a given collision multiplicity, we were able to take V2 data from RIC and basically, from the uncertainty that we estimate from these coefficients, make a band for the allowed relation between the beta 2 of uranium and that of gold, and we take this orange line. And then we notice that if one just takes the value of beta 2 from the measured spectroscopic data at low energy, then you get something which is fairly off. It is this blue box. And this is essentially consistent with the fact that, as I said, hydrodynamic simulations seem not to capture the specific ratio if you look at the existing comparison. It was recently realized by Vato Ressens, actually, back at our meeting in Heidelberg, that the error here that we were doing is that we were essentially mapping directly the measured beta 2 coefficient to the one which is related to the intrinsic Wood-Saxton shape that we used in the model, whereas actually to the total beta 2 of the system contributes as well a coupling, in particular between beta 2 and beta 4. And so whenever you have a nucleus that has a large beta 2 and a significant beta 4, and this is precisely the case for uranium 238, you should not just map these two, but you have to take this subleading correction into account, and this leads to a reduction of the actual beta 2 Wood-Saxton that you should include, which actually goes down from 0.28 to 0.25. But this is actually then precisely pushing this blue band inside something closer to RIC data. And these red box with these points are results from 21 different SCRM parameterization for mean field calculations of uranium 238, which all gives consistently beta 2 for both uranium and gold, which is essentially on top of the one the constraint with the Raptor brick. And so there is this reduction of the beta 2, which is something very interesting, because it implies that when you talk about these intrinsic shapes, then you have also to be very careful by taking into account how the various modes are correlated whenever you have large deformations. So the impact of this beta 4 is indirectly observed by this reduction in the beta 2 Wood-Saxon, which is then we also have idle simulations ongoing with Bjorn Schenk and Chun Shen, but so that they now get a good description of actually the weak data. So this correction was missing. So the decapole does something like that. Going back to the quadrupole, we also realized that the triaxiality can be inferred from the same row correlator, ship size correlation, which is something.
Oh,
yes.
Can you go back to the last slide? I must say I did not fully get what the difference is between beta 2 and beta 2 with Saxon.
Beta 2 is what is reported on measurements. So what is like from your spectroscopic transitions, they quote some beta 2 value, which is something that you typically measure, assuming like some rigid rotor, etc. And this is what has been implemented in hydrodynamic simulations. But once you go to the actual Wood-Saxon parameterization of the system, then that doesn't map so straightforwardly whenever you have a significant beta 4. And this is the case for uranium. So beta 4 is also measured at low energy.
Can you illustrate that? Go back one slide. I think you had a formula there. Yeah, so this beta 2 up there, is that what you call the beta 2 with Wood-Saxon or the other one?
Yes. It's the intrinsic shape that's used for the simulations.
Okay.
Yeah, I will try to explain this difference in my talk.
Very good.
Thank you very much. So yeah, indeed, I'm pretty sure someone else will also cover this. Thanks. Now, if you play the same game that I showed before about correlation between size and the ellipticity of the overlap area, you can realize that while it works, as I said, for prolate nuclei, once you go to oblate nuclei, the situation is reversed in the sense that a large area corresponds to a circular system and a small area is elliptical, whereas on the prolate case, it was small circular and large elliptical. And this means that the correlation between the size and the shape is sensitive to the triaxiality of the nuclei. There's this nice leading order behavior which was figured out by Giacalone. So it actually goes really pretty much like this. Then we had the candidates to see this, which is xenon. So Benjamin Bali, Michael Bender did the calculations, state-of-the-art calculations for the ground state shape of xenon, and turned out to be triaxial. Now, what happens at high energy, we have precisely this row observable, which can see how it deviates between xenon and lead collisions. So this would be departure from the baseline. Again, this is the experimental data recently released by Atlas. These are theoretical calculations, theoretical expectations from the Trento model, and the ratio is actually quite accurate because many systematic scans as you take a ratio. Now, the spread in theoretical curves that you see in the limit of zero centrality, which is again fully overlapping shapes, is due to the variation in the gamma parameter. So from basically prolate to oblate nuclei, and the consistency with data is actually obtained for triaxiality, which is precisely what was predicted by this EDF calculation. So it's very nice. This will be, I think, confirmed by hardware simulations in the near future, and seems to work very well. Then it comes, so we see again also quadrupole, triaxial, hexadecapole. Then there was this breakthrough in 2021 by isobar collisions. I think next week is entirely dedicated to this. So I will not spend too much time here, but the idea is precisely that you have these systems which collide nuclei of the same mass. So XX and YY are essentially the same QGPs, if you want, up to the shapes of the nuclei. So the ratio of observables taken by these two collision systems is not really one, because there is nuclear structure, and this can be mapped out very precisely. So what has been observed, the most straightforward thing is the quadrupole deformation of ruthenium-96, actually. So again, if you have your leading order correction to V2 at a given multiplicity from the beta 2 squared, then if you take a ratio between what this thing measured in ruthenium and this thing measured in zirconium, so the fact that these two coefficients are essentially the same gives you one as baseline, which is what is here. And then the correction comes with the difference of the squared of the deformation parameters. So what is measured experimentally, these black points are the ratio of V2, exactly like this. And you see that in the limit of fully overlapping shapes, central collisions, this has this sort of dramatic increase like this, which is precisely isolating this correction to unity. So it's up to 10% correction due to the larger beta 2 of the routine, which is something measured at predicted by low energy physics. Just taking at the spectroscopic table. In this case, there's no real issue with the hexadecapole because that should be really small. So this is very straightforward, and this explains just in model independent way essentially the data behaves like that. Now the big surprise was that you see in the ratio of V3. So this is the third harmonic, so the triangular shape of your system. You see the same kind of very dramatic behavior here. Sorry. Which in this case is below unity, meaning that is actually the deformation of the zirconium, which is winning, and that should be, sorry, much larger than that of the ruthenium. Now, as far as they tell me, I think there will be a seminar by Magda Zielinska next week, precisely on this. There's no experimental information about the octuple deformation of ruthenium-96, whereas there are a few measurements on that of zirconium, which is in fact something which should be very significant based on transition probabilities. So it's very interesting that this is also seen somehow in the trick very, very clearly. It has to be like this, essentially. I hope maybe Katrin will comment also more tomorrow about whether this can be perhaps measured for ruthenium. But one question I had is whether nuclear theory can actually predict something like this, so this ordering. So this was one of the main driving points for having an ME task force this year in Heidelberg, which was successfully held in 2 meetings. So the difficulty with the octuple deformation is that it's not something you get in mean field. So in all calculation that doesn't show up for this nuclei, essentially. There are a few for which shows up, but very few. So you have to do beyond mean field calculations, including octuple parity breaking, essentially. And this is what they tell me is that was not really done in this region of the nuclear chart. And so we got new calculations done by, for instance, Luis Robledo, Tomas Rodriguez, and now also by Juan Bali, who is in the audience with this new ab initio projected general coordinate method analysis, which I think you will talk about that again this week. We have very promising results in the sense that once you actually go beyond mean field, if you look at the energy map and you try to look where your minimum beta 3 is, you have something which is very deformed after symmetry restoration. So you almost confirm the beta 3 of about 0.2 at least here for the zirconium-96, which is exactly what we wanted. Much smaller value minimum for the ruthenium, and I find this very interesting. Then, according to what these people told me, there is a very strange phenomenon going on here, which is that the restoration of symmetry, projection onto good quantum numbers of angular momentum is giving you a big correlation energy. So it's larger than a 10 MeV correction, which is something unprecedented as far as I'm concerned. So I find very nice that we have been able to somehow push really nuclear structure to the limits from motivated by high energy observations. But this seems to be working in the sense that what we need is sort of now being confirmed. So we will have final results later this year. Very good. So I've discussed quadrupole, triaxiality, octuple now, hexadecapole. Now there is a sort of bonus, which is the possibility of seeing the radial profile, the skeins, which is a big topic in nuclear physics. This again is something which shows up very naturally in the isobar run. So zirconium, as Zhang Yong anticipated, has more neutrons than ruthenium. So it leads to a surface that actually, so this black line is sort of less sharp than this red, which is the ruthenium. So there is a difference in the, if you want, the slope of the fall-off of the density, which is due to the different scheme, neutron scheme essentially. And this is a parameter in the Saxon density. So this difference is now observed in many ways in different observables in high energy isobar collision. So what was discussed even before the run was in particular the effect on the multiplicity distribution. So this is probability of multiplicities in ruthenium collisions over that of the zirconium collision. There is a characteristic sort of S shape, which is captured by models when they include the difference in skin. So it's actually coming from that. This is sort of established. And the different second observable, which was intensively studied, is the mean transverse momentum. Again, so as I said, it's something which quantifies the size of your interaction region. so the more diffuse surface leads to a larger area for zirconium collisions and the slightly lower transverse momentum as a function of centrality. So ratio of mean PT, see, these are full hydrodynamic simulations actually, which have we're able to go to this precision. It's really, really precise stuff. But so they see something which is above unity if they include the neutron skin, the larger neutron skin of zirconium. And this is consistent with the observations, actually, though I think I'm not allowed to show those here. But if you don't include the large neutron skin, actually this drops to something which is below unity, which means that then they did also possible variations with this colored line of deformations and other things, but there's never qualitative change as this one due to the neutron skin implementation. So this is really probing that. There was also another very comprehensive set of hydro simulations from the group in Ozhou, and also Fujiang, etc., where they also checked how these ratios depend on different implementation of viscosities, and so these are very robust and seem to isolate initial state information, which precisely this neutron skin difference. Then for the heavy ion practitioners, I would like to also point out recent finding of very clean manifestation of the skin actually in the reaction plane flow. So if you remember the Gaussian model of elliptical fluctuation, so there is the reaction plane flow, which is basically the average ellipticity you get because of the impact parameter. And this quantity is something which, of course, grows as a function of centrality. And it has to be somehow sensitive to the skin of the nuclei because it depends on how sharp your ellipse is, right? That was determined. And so this V2RP, the reaction plane flow, is then can be essentially estimated with this V24 cumulant that we can measure experimentally. And so here we plotted in EMPT simulations V24 of ruthenium divided by V24 of zirconium. And so if we just mess up with the deformations of the nuclei, we don't generate any sensitivity to this ratio. So beta 2 and beta 3, they don't really change this ratio. But if you then add the fact that there is a larger skin in the zirconium, then you get this bump, which is consistent with the black points, which is start data. And so this is very, very clean. Also, I would say physically motivated evidence of the larger the effect of the skin of the zirconium being larger than that of ruthenium is very, very actually. Always seeing on skins, I would like to highlight this analysis of STAR, which will be actually covered in the last week of the program by Daniel Brandenburg. It's a paper recently published in Science Advances, which has in less than 1 month had made 12,000 actually downloads, which is remarkable. So this is the idea of probing nuclear densities, actually gluon densities in ultraperipheral collisions. So there's photon splitting in quark and antiquark and interacting with the nucleus, and then giving you a rho zero vector meson. And from the momentum of these particles that you can reconstruct, you can actually see that the distribution depends on the Fourier transform of the gluon density of the whatever is in the nucleus, which, for instance, again, Wood-Saxon. And this is a technique then with playing some games with the particles that you observed, you can reconstruct, in fact, this Wood-Saxon. And in particular, then, since you know some about the charge density from low energy physics, you can actually try to measure the neutron skin. And this is what they measure for the skin of gold 197. So a very nice result. Which is fully consistent, in fact, with what state-of-the-art nuclear theory predicts. We had a paper on January with the new beyond mean field calculations, and we got the same number, essentially. So this is a very promising way to see skins. This could be done as well at LHC with the lead nucleus, which maybe would have been a bigger impact. So this concludes essentially my review here. So we see everything. We have identified observables that isolate the impact of various deformations and shapes, as well as the skins. And for the moment, all we see, I would say, in high energy data is consistent with what you expect from low energy physics. So you have confidence that the way you are modeling these collisions is appropriate. And there are no clear indications, I would say, again, that there's something is strongly modified by going to high energy, although that would be something which would be extremely interesting to figure out if that happens or not in further detail. And so this for me is what to set the stage. So if I still have right, I have a slide that I would like just to make this comment, that in conclusion, this essentially once, let's say, this gives you effectively a method to image nuclei to get evidence of the shape of this nuclei, and if you think about the sort of ultimate nuclear shape experiment, at least for these ground states, if you were to explore like well-deformed nuclei systematically, then you would see an infinite amount of things. You could precisely determine relative deformation between very deformed nuclei, so up to percent level precision probably. So you would see again these sort of isobar ratios going between plus, or let's say, above or below 1. So this will give very fine information. You could see small triaxial deformations on top of very large quadrupods, which I think is essentially not really measured in low energy nuclear structure experiments. You could even think about, since now we understood that there is effectively, once you study very deformed nuclei, you have to make sure you couple all higher order harmonics to the quadrupole. So you could even have evidence of beta 6, for instance, which would be really interesting. And this will give you model independent most of the time for new constraints for new state-of-the-art calculations of nuclear structure. And overall, this would be complementary knowledge about nucleus. So even though maybe you want to use colliders to do this, but still, this seems to be very solid information that we have learned from high energy nuclear experiments, and I think it's interesting. Now, if I still have 10 minutes, I would like then to talk about prospects. If there are no further questions up to this point. So I think most of what I've said will be in some way reviewed in this program. So prospects, I think there's plenty of stuff that has to be done then in future. So the most obvious things for heavy ion physicists is that it should be possible now, for instance, observables like this, which show very, very strong dependence of the deformation parameters, to make a real extraction of the deformation of uranium, for instance, or xenon. Maybe that's even easier. From high energy data alone. So this would imply promoting the deformation to some parameter of your model and then incorporating that like in the Bayesian analysis, where you try to extract posterior distributions of parameters. And then see to which extent you are able to reconcile what you see with the low energy expectations in a way that does not involve any input from the low energy side. So I think you will get pretty much consistency, and this is something to be seen. I think it's going to be exciting. So going beyond shapes, then we've had a lot of interaction also. We are starting having interactions with the community of people doing ab initio nuclear theory, where they don't necessarily try to encapsulate correlations in shapes, but they really try to provide solutions as accurate as possible of Schrödinger equations with some Hamiltonians motivated by low energy limit, let's say low energy effectivity theory of QCD. And I think it's very nice to. There will be the fourth week of this program. We'll have a lot of contribution from the ab initio side, and we will see what we can do. So the idea is really again to have really an input from just correlations between nucleons from these state-of-the-art theories of nuclear structure. So there is already something going on in this direction, and this is something which is timely because we will have data from oxygen-oxygen collisions at both RIC and LHC. And so we can, this nuclei can be computed in several ab initio frameworks, and we can already see what this thing gives. So this is work in preparation. So for instance, what we have for the moment that has been used as input for heavy ion collisions are 16 O nuclei from two ab initio calculations, one within the variational Monte Carlo simulations with this argon-Urbana interaction, which is something which has in fact a repulsive core, short-range repulsive core among nucleons implemented. And then there are configurations from nuclear lattice effective Tier simulation, which were provided by Dean Lee and collaborators, where the interaction is actually simpler. So it is in fact a very low resolution, but they have a very good many-body solution for their problem. So now if you take these two frameworks and input them, so BMC, the first one, and NLA EFT, second one, you input them to oxygen-oxygen collision, you can see that we have a spread in V2. So this is very interesting. It's essentially a 10% difference between the two models, which then will go into any uncertainty that we have at the level of the initial state or final state of, let's say, our understanding of oxygen-oxygen collisions. So this is a very, I would say, nice way of quantifying the theoretical uncertainty that we get on top of all the rest, just from nuclear structure. What is interesting is to understand better why these are different. So difference comes from n-body correlations. So there is a repulsive core implemented, which is absent here. How much this is modifying this? or again, this has a superior many-body solution, like how you solve the Schrodinger equation, how you sample the nucleons essentially. So is that more important otherwise for the more many-body collective nucleon correlations, which are more responsible perhaps for V2? So we have to investigate this, and we are making the first steps. I think also an obvious application of nuclear structure to let's say help or inform high energy collisions is exploiting this beautiful nucleus, which is neon 20, and in combination with the oxygen 16 that we will have. So neon 20 is close in mass, so you can hopefully try to play the same games that you played with the isobars that I discussed previously. I think this will be discussed in week 4 by Jean-Paul Lebrun. Neon, oxygen, very different geometry at multiplicities that are interesting for us, because this is some of the place where we want to try to understand better where the flow is originating in heavy ion collisions, because this effective hydrodynamic description is not really expected it could potentially break down once you go to these much smaller systems. But this is exactly what is going on there. We have some results from large-scale actual hydrodynamic simulations that within the trajectory framework, where yes.
Can you go back? Are the plots on the left mislabeled because it says integrated rho over x and it shows it as a function of x?
You're right. See, this is the old version which was wrong, and I forgot to replace it. Thank you.
Okay, thanks.
That's precise. So, very good. So these are in fact the thickness functions of neon. Yeah, thanks. Yeah, there it's wrong. Thank you very much. So we did the large-scale hydrodynamic simulations in the trajectory framework, and to see what difference you get between oxygen, and neon. And it's very sizable. So this very extreme shape of neon essentially survives the final state, because even which is, it's non-trivial, I would say, because once you go to these few nucleon systems, then you have these huge fluctuations in just the nucleon number, and that's not necessarily true that you will see an effect. But this is clearly surviving, at least to have a 20% correction to the V2 of oxygen-oxygen collisions, which is entirely coming from this geometry. And there are 2 points here that I would like to make. So first, this is now computed within ab initio nuclear theory. So it's a bit horrible at the moment, because we have 2 different frameworks, one for oxygen and one for neon, but we are getting, there's a guy in the audience who's about to compute the oxygen in the same framework as neon, so we'll have more consistent results. Of course, it's very interesting to study the systematics of different ab initio results and see what they give you. But otherwise, you have what we see is a 20% effect on the V2 at these multiplicities, which are of order 100. So it's pretty much the multiplicity of central proton-nucleus collisions. And my point actually is that central AA like this, light ions, is actually more robust than other effects of this kind that have been observed as signature of an initial state geometry in small systems. And I'm talking about proton gold versus deuterium gold. There are the enhanced V2 observed in deuterium gold by both Star and Phoenix. I think that relies quite a bit on how you model the proton, actually, because that's what you have to do. And they showed that there are significant differences among, for instance, theoretical interpretations depending on how you model the structure of the proton, which is something that you know very little about it. Okay. The same kind of effect will be observed by comparing central oxygen versus peripheral lead-lead. So peripheral lead-lead has an intrinsic ellipticity, whereas central oxygen has not. Okay. And so this will have a larger V2 than this one. But then these 2 systems are very different, because one is like a blob, a circular blob, and the other is a very elongated medium. So actually they are the same multiplicities, but for instance, they have different longitudinal structure for sure. And I think it's less robust than having central AA collisions for 2 systems. So this idea of doing an isobar ratio somehow is, I think it's still the best. And just one comment, these band are essentially the result from millions again of hydro simulations, where we have varied very extensively the parameter space, like eta over s, zeta over s, initial state parameters, pre-equilibrium parameters and such. The ratio of the V2 is actually a systematical uncertainty due to model space variations, which is only a few %, which means that there is this number which is predicted by ab initio nuclear theory, and this is what you get in the hydrodynamic model, and this is really what you want to see if you get the same number in the data, essentially. And hopefully, again, this is ab initio nuclear theory, so it should be very precise, and so you don't have much of an uncertainty on the nuclear structure, although this is still to be established, because we need more input from them. So neon is very good. My hope is also that we can also, this is also again work in progress. There's Pragya Singh who will give a talk on this topic essentially in the second week. Whether neon could be a good candidate to see the role of small X gluons as you boost to high energy. This is very exciting. So this would be again the thickness of neon at some collision at some energy. For instance, let's take 70 GeV. Corresponding to some low X, then does it keep the same shape if you go to much lower X and go to full LHC energy, for instance? Now, the good thing is that something this could be actually tested almost immediately if you collide neon, because neon is already in the smoke system of LHCb detector. So it's this gas that they inject to do fixed target experiments, which end up to be at a central mass energy of about 70 GeV. So there is a factor 100 from what you get from collider mode. And this will allow you really to see if there is an effect of the small X evolution on this shape, on this sort of bowling pin shape. And Pragya maybe will show some results on this. But also the planned focal upgrade of ALICE, which would allow you to study neon collisions, for instance, at forward rapidity, where you can compute a V2 at forward rapidity, which will allow you to probe one neon at small x, one at large x, and hopefully see some effect of, again, small x evolution. So this is exciting because it will be the first time, let's say, evidence, if it turns out to work, of the role of cogs and gluons for, let's say, the collective shape of a nucleus. And that should be very exciting to see. To conclude on this, I was at a workshop last week in Hirschegg in Austria with a bunch of, it was essentially a workshop of effective field theory for nuclear matter. And I found very interesting to see that in this business, they actually do Bayesian analysis. So it's something that they started pretty much in parallel with the heavy ion collisions, so heavy ion physicists, where they actually try to get from a large sets of data the low energy constants of the effective field theory. So this is one such calculation, which reminded me a lot what we do as well in heavy ion collisions, where we have our model and try to constrain parameter from Bayesian analysis of the experimental measurements. And I think it's very exciting in the future, that possibility of making contact, in a sense that try to provide to high energy modeling better and better nuclear interactions, and may perhaps see different parameters, what impact they have, and things like this. So I think the connection with the ab initio community can be very, very prolific, and I'm looking forward to working more on that. So my prospect for experiments then, whether there's more to do with respect to what I've already discussed. So I think I learned recently that there will probably be possibility of colliding more species going to lower masses at LHC in 10 years from now and beyond. There's a technical reasons why they might want to do this. This could be a very nice opportunity. So it will be really nice then to again discuss with the nuclear structure community and figure out what would be the optimal species, but to maximize essentially the output of these runs for, I would say, the entire nuclear physics community. One obvious suggestion then, based on what we have learned, whether colliding nuclei that are close in mass, like calcium argon, would be the right strategy to follow, because then you can assess again the sort of isobar ratio, where you look at very precise variations between systems, and you can learn quite a bit of that. So this is something that we have to work on. Zhang mentioned EIC. I think my opinion about this is that this is again a very precise nuclear physics experiment, which means that you have to be careful with these nuclear shapes because they will show up probably in some way. And this is a way to, I would say, assess that you understand what's going on, and you making sure you can perhaps improve the science cases. So I think my understanding is that there will be naturally an interest in colliding different type of ions, using different type of ions, because they have to gauge the A dependence of the nuclear modification of the parton distribution functions, for instance, which is done by hand right now, if I understand correctly. And of course, it would be nice to see how this kind of features are modified when you have shapes. And okay, one I would say most straightforward idea is to keep the same A and change shape. So this is, for instance, this chain of samarium isotopes does precisely that. 7% difference in mass, but shape goes from spherical essentially to more deformed, much more deformed than the uranium actually. So this is something. So week 5 of the program is about the connection with EIC physics. So I hope to start some discussions there too. So nuclear structure for energy nuclear physics. Then this is what I wanted to say. So So my summary, just that precisely multi-nucleon correlations in nuclei, they will show up in multi-part correlation in the final states of the ion collisions. We have an high energy model, which is based, as Uli correctly pointed out, on certain, I would say, assumptions, but we can still try to test it more and more with more refined input from the low energy physics to see how far we can go and how much we can understand. It's of course very nice to have different nuclei, because you can have these very nice impacts of different shapes and such in your initial conditions that then allow you to check for consistency. And so everything shows up at high energy, and hopefully we'll see more in future. So theory, I think we want to get more and more input of all kinds from nuclear structure community. So I've discussed large nuclei. We still have very, very little input from, let's say, how can I say, systematic calculations in energy density functional, for instance, mean field calculations. We could get hundreds of initial profiles for nuclei, and we don't have that yet. Hopefully we will have, just to see what is somehow the spread in the theoretical error, essentially on the shapes of nuclei. And then we should also try, as I said, to try to extract directly from high energy data some information which can be compared with low energy. The connection with ab initio community, I think it's going to be great, because they are pushing to higher masses, and they will provide superior inputs, probably rooted in QCD, and we can play many games there. Experimentally, there are many things to be discussed, and see what can be done at colliders and EIC as well. So I think this is all very exciting. So I thank you for listening. I hope I'm on time. And then enjoy the program. I will be there at some point later in the program, but thanks.
Not out of time, but still, if you have some question, we can still have. Enter them on the Google Doc, but also we can discuss briefly. Go ahead.
Yeah, I mean, I'm sorry for monopolizing the questions here, but if you could go back to slide 36. I would like to make a comment there. I think this approach is very important and very promising, but what you have on the board doesn't do justice to the complexity of the issue. Sorry, Matt. Because when you look at that, there is room for including experimental uncertainties, but there is no room for including theoretical uncertainties. So if there is an underlying assumption in these equations here that we know the theory that projects the system from the initial nuclear configuration before the collision into the finally measured spectra and anisotropic flows. And there are obviously uncertainties in this modeling that need to be included. And this is not happening in a systematic fashion yet in any part of the community. We are beginning to do that, but I think an important ingredient will not be only the uncertainties in the evolution of the fireball, which we have gotten some handle on over the last few years, but also the uncertainties in the transition from the state at tau equals 0 minus to tau equals 0 plus, which I think has been almost completely unexplored at this point. So I'm making comments because we're at the beginning of a 5-week workshop, and I think we should keep a few questions in mind as we discuss these issues.
Yeah, thank you. This is very relevant, of course. What I can say is that, well, we can use a sort of phenomenological ansatz like you do in the Trent model. And if you try to extract, for instance, the deformation of uranium from a data like this, you will be able, I believe, to spot potential correlations of parameters, like whether you extract the same deformation, whether P is equal 0 or P equals 0.5, and how correlated these things are. And I think already having that information will be a very good starting point.
Juliano, maybe we can have that discussion in the afternoon. Because there's few more questions. We take this as, but it takes a lot of time to answer that. Okay, so thank you.
I have a very naive question, I think, related to what we just heard about the evolution from T minus to T plus. It's very naive, so please let me know if this has already been thought through. The electromagnetic fields or any other long-range field that the two objects experience before they actually have strong interactions must have some influence on the orientation and the position of the nucleons. Is it just too fast to respond to the electromagnetic field?
My understanding is that precisely there's too fast to experience Coulomb interactions essentially on the magnetic field of the two nuclei. So this is why, for instance, we don't have any reason to believe that these nuclei are not in the ground state, for instance, because they're too fast.
So, okay, it's a very simple estimate, and you can see that the response is negligible.
I would agree with that.
Oh, but we need some to see that maybe
I
explicitly.
don't know
Right?
if anyone wrote it down, but yeah, the amount of time that passes between when the electromagnetic field becomes appreciable,
Because they're all compressed.
when they actually collide, it certainly is an extremely small amount of time. So I don't know what kind of process could happen at that time.
Exactly.
It would like rotate an entire nucleus.
So the key is that what you think of as very long range, really long range in the Z direction because of Lorentz contraction.
Yes. I think the time scale is really crucial here. Everything here is faster than anything else in the nuclei, and this is why this is so clean. There's really this snapshot. So.
Okay, are there more questions? First of all, people on the Zoom, please feel free to ask questions anytime. Okay. So I already copied a few questions from Uli on the Google Sheet, and so I will populate something there. But yeah, please feel free to add. Okay, so I think that this is probably the end of the first talk. Let's thank Giuliano.